Slicers are almost useless because most of the features inside of them should actually be designed inside of CAD. So in this video, we're going to go through and show you how you should be designing the Raft, the Brim, and actually the support in order to minimize material and make sure that your parts print correctly every single time.
You really should not be using a slicer to make brims. They actually really suck at it. So in this video, we're going to talk about how to actually do a brim correctly and how to not have to use a slicer so you don't have to rely on that piece of garbage just messing up your part. Now, when I say messing up the part, I do mean that. If you place a brim onto a part, what you end up with is a bottom edge that has either marred up from any sort of deburring that might have to be done, or potentially just a place of weird extrusion because you have the brim left over there. But the brims are very often necessary. If you're making a part with really sharp or thin tendril-like features, you kind of need a brim because those features can't just necessarily reliably stick to the print bed. So you need to give them a larger surface area so that they actually can stick to the bed. Everyone always flips on the little brim feature inside of the slicer and the brim pops out. But then you spend tons of time cutting at it and polishing it and sanding it and cleaning it up and that kind of stuff. And in the context of things like our print-on-demand applications where you can upload a file and then have the product shipped to your customer on like your Etsy or your Shopify store, that can introduce the opportunity for problems because you introduce the chance for some sort of error to happen. And the more brim there is to be removed, the more opportunity there is for that. So you really actually want to optimize the brim, especially if you're going to make a million of these things. When your product catches and you actually have to mass produce it, you do not want to be pecking at the brim for an hour for every part. It increases cost, it wastes your time. You want the brim to be optimized, and there is no way to do that inside the slicer. Slicers are terrible at almost everything. Their job is to turn a 3D model into machine motion. Once you start using a slicer for CAD itself, where you're trying to make thick walls and give it a brim and have a raft and have it generate new features, you're now following into this generic profile that just is not very reliable and cannot catch all the situations that you're going to design for. But you can catch all of those in CAD. So this is why we want to talk about brims in detail. Now, if you're designing a brim inside of CAD, the first rule is make it 0.2 millimeters thick. This is a nice generic catch-all. You can make it up to 0.3 too, that's okay, it'll still appear inside the slicer, but 0.2 is also a good catch-all, and then you can know it's thin enough. You do not want to make it thicker. If you make it thicker, it's now more than one layer thick inside of the print profile, and if you upload it to a system like ours, then it would definitely be a couple layers thick if you made it like 1 millimeter through. Now that is no longer a brim to be removed, that is a feature that is a part of the part, and we're not going to touch it. So just make sure it's very thin. The very simplest brim that you can do is a single shape on the bottom of your part. So like in the case of this star, you can just make a circle underneath it. You can also make a square, but a circle is better because rounded features on the build plate are easier to print because they don't have peel out points. You're trying to eliminate corners as much as possible. So a circle is the best way of going. You take that, you extrude it up into the part, and now you have a brim. It's an oddly shaped brim, but a brim nonetheless. And here's the very unique feature of this. With traditional auto-generated brims, they basically create multiple perimeters of the part on the outside. And then they print to the part itself, which has rastering in the side-to-side bottom infill pattern. The problem with this bottom infill pattern and with this outline is that the outline format can sometimes create pull-up and all sorts of other sorts of issues. And then the rastering itself creates a point of separation and some weird looks. Basically, there's a mismatch between the bottom of the part to where it can't really all adhere because it does the outlines and then it does the infill. It's much better and you have much better adhesion if you have long continuous lines where there's not interruption in the pattern of the part. That way you don't have to worry about deviation or bed adhesion issues if you're dealing with complicated materials. So by modeling the brim, you create a single uniform bottom layer. So this whole circle that we just created is printed as one single pass that is trimmed off, which means that it prints very reliably and you don't have weird little tool motions that could potentially disrupt your first layer. This is a really big benefit of using designed brims rather than using auto-generated brims, even beyond all the other issues with it. But This is kind of a brute force way of doing it. Putting a big old cylinder underneath the part is a nice clean way of doing it, and if you're not really deep into modeling and don't have a lot of time to put in like a complex part, it's a good way of doing it because it doesn't create that many issues and trimming it off is not a big deal. With these brims, however, if you're running it through an automated system like one of ours for like Shopify or Etsy, just make sure that you like put the word remove or something on it so we know that it's not an intentional part of your part. And as we do more of these, we need to be able to differentiate. So if you can put a remove on there, that gives us the signal that that is a removable feature of the part. Now, there is a simpler way of doing it. If you have a nice symmetrical part, like in the case of this star, you have these really sharp features that need to be tied down, but it's really only the tips of the stars that need to be pulled off. And the rest of it on the internal is really in the way, and again, it's just adding labor to it. Removal of all that stuff is cumbersome, and it's just not helpful. So rather than doing just a big old circle that encompasses the whole thing, do an outer ring. And you can modify these and design them in different ways, but that outer ring again creates a nice uniform first layer. If you are printing at home, you can use something like a concentric pattern so that you have a nice outer ring that's reliably put down just like a normal brim, and then it's very quick and easy to remove. Those are the two simplest ways of creating a brim. But one subtle thing, a brim adds material to the first layer of your part, which means that area can potentially be wider. If you want to make sure that a brim doesn't leave an artifact on your part, regardless of how good the post-processing is, what you can do is design the part correctly for 3D printing. In every video, we talk about applying a chamfer to the bottom of your part. This is even more important when you are using a brim. We have a 0.2 millimeter brim coming up into these parts. What we applied was also a 0.5 millimeter chamfer. What this does is it has the point of contact of the brim slightly in from the outside of the part. And that chamfer also serves as a guide area for the blade that is trimming off of that part. This makes sure that the brim doesn't add more material to the part. And if it does, it's not noticeable. It goes from a slightly chamfered edge to a square edge. So this is a good way of having a part held down with a brim and ensuring that the brim does not mess with the tolerances of your pieces. Applying that chamfer makes sure that the brim can be trimmed off, and if for some reason it's not perfectly trimmed off, it still creates a reliable part without overhangs or elephant footing coming out the side from that brim contacting it. It also has the dual benefit of that chamfer and that brim coming together, creating a stress concentration right in there, which means that now the brim can be more easily peeled off because it has a very tight break point created inside of it. And you can play with this a little bit more. If you want to go into super advanced brimming, you can make the brim actually thicker away from the part and then thin at the point of the part so that basically you can just pop it straight off. But that's beyond the scope of this video and is not always useful. But I'm going to throw it out there as a tidbit for you anyway. Comment down below if you want the follow-up for that. Now, sometimes you don't have a nice simple shape like a circular star. Sometimes you have something weird that's going off in all kinds of different directions and you have one little tendril sticking out the side. In this case, you want to use kind of a subset of a brim called mouse ears. Mouse ears, we've done an entire video about the actual design of these. They are a very specific feature that can be used in all kinds of different ways. Now, very quickly, for the purposes of this video, a mouse ear is basically a circular tab holding down that edge out there where it's needed so that you have a lot of surface area tacking down that area of the part to the print bed. This eliminates the problems with warp a lot and is very useful. The problem with mouse ears is that they do have to be manually placed, and if you have a really odd looking part, it can be a lot of work. But again, if you're making 1 million of these, you want to design them correctly. So those are the generic types of brims. There's big old shape underneath the part. There's kind of a refined shape where you start minimizing the contact area of the brim. And then there's individual mouse ears if you have just an odd part where there's particular localized areas that you need to hold down. We have talked about many of these features before. Like I said, we had a video about mouse ears, and of course we've talked about rafts in our other Design For videos. Ultimately, a slicer is a really bad way of creating features. These features are kind of lazy add-ons to help compensate for an inferior process in the olden days. But if you are able to design for it, you should design as many of the ancillary features as you can so you know you get exactly what you're looking for. Because as systems scale up and people use print-on-demand tools like our API and those kind of things, having more control of the CAD ensures that you're not beholden to whatever our settings may be for support. That way you can optimize your design at home and know that whatever goes through the system will still be what it was that you designed. And you don't have to go through an iteration process of trying to adjust to the features of the slicer or whatever it happens to be. The slicer cuts the object, creates layers of that 3D model, and does it within tolerance. It doesn't add features, it doesn't move anything around. It's just what it is. You can create something much more optimized, much more reliable, and something just better that has less labor and a better quality output than what those generic menu items are that pop up inside of these slicers. So rafts are a very common and very useful feature inside of 3D printing slicers. They can protect the base layer of your 3D print. They can compensate for any sort of variation in leveling on the bed. They can make sure you maintain high tolerances on the parts, and they can help to keep the part stuck down to the bed without having significant post-processing like brims and that kind of thing. But the issue is that slicers are freaking terrible at making rafts. Here's the issue. So most rafts are designed with a rastering pattern on the base layer so that it can be removed from the bed easily, and then multiple layers on top. Many slicers are really bad at defining how these features work. And since they are dependent upon the slicer that is made on, it's very difficult to prototype a part and then send it into mass production at a giant print farm like ours. Our slicer might be a little bit different from yours. The spacing might be a little bit different on your raft. The cooling might be a little bit different. All of these factors really affect how the raft performs, and they are really ambiguous about what they are. How thick is your top layer? How thick is your first layer? So on and so forth. All of this is just kind of silly. And if you're running through like an automated system, if you like submitted something through our API or our Etsy plugin where it's blind and the part is just sliced and then printed, you don't really want to have to rely on print settings. You want to make sure that you control how that part is going to come out so that it's really, really reliable. And the only way to do this is inside of CAD. But let's talk about regular rafts just a little bit. Not only are they not user-friendly and not consistent or reliable across platforms, but the way they're designed is incorrect. Many of them have the rastering pattern. That rastering pattern is generally one large bead of plastic. When dealing with high warp plastics, such as ABS, that large bead creates a really thick concentration of material that then shrinks. So the raft itself peels up from the bed and creates stress concentrations and stress forces, internal forces inside of the raft that make it want to peel. It's a really bad way of designing that first layer. They should be thin and small, but you can't do that because the raft has to stick down to the bed. The subsequent layers also on many slicers are spaced out too much, and you can tune these, but it's very difficult to get them to where they need to be. A lot of them are kind of stringy because they're like, oh, the raft needs to peel off easily, but you end up peeling off and leaving material on the core part. And inside of slicers, when you're spacing the raft, the part can often become disconnected from the raft itself so that you can remove the raft, but then the part isn't actually cinched down to the bed, and you create all of these issues. So, the best way of fixing all of this is to design a raft into the part itself. It's not difficult. At the most basic level, you can just create a plane, a sheet that is then printed underneath the part. This gives you the reliability of the part, the strength of the part, make sure that the part is cinched down well, make sure the spacing is all there, and you don't have to deal with fiddling the settings inside of a slicer that might be ambiguous. Now, that doesn't fix any of the other issues with the raft, but let's start with a cube. First of all, make sure you fillet the vertical edges of the cube. That improves print quality and print speed, and you do not need sharp corners anywhere inside of a part. So you put the plane underneath it. That plane generally can be spaced out by the distance of the layer height that you're using, maybe a little bit less if you want to increase adhesion. So if we're printing at 0.2 layer height, go ahead and space out the designed raft 0.2 from that part. That's the baseline, easiest thing to do, super simple. Make sure the outer edges of the raft are rounded, again, as much as possible. If you could put a circle underneath the part, that's ideal, because then you don't have potential areas where they can warp. Sharp corners warp on a first layer if you're dealing with those types of materials. Now that's the very basic and most simple type of raft you can possibly get. Now let's get a little bit more interesting. This raft is not holding down the part. You have to tune spacing. That's a little bit too much effort. The corners of the cube could warp and peel up from the raft, so let's go ahead and just tie those down. What you can do is you put some small 1mm struts underneath the edges of the part so that they are physically connected to the raft, and now the raft can hold down the part and serve as increased adhesion holding down the piece. But when you remove the part, they're 1mm struts, so they're very easy to either snip off or just manually break off. You essentially create a very simple zipper that's able to break away, and then you can still have good strength adhering to the raft, but a part that's easy to remove and process. But now let's go ahead and go to the raft itself. The part is stuck to the raft well enough now, but the raft itself now has to stick to the bed and be reliable. Like we said, round the outer edges, that's great. A lot of problems though with rafts is that the rastering is very often linear on any of these parts, and when it's linear, you have that shrinking problem again, where there's a big old long streak of material that then shrinks and causes the raft to warp. In order to fix that, break up that big old long streak of material. You can do it by just removing a very small section of the base layer of the raft. You can do this by just putting a big old circle underneath and pulling that up like 0.2 millimeters again, so that you just lose a single layer, so the raft is still sound and the raft can still potentially kind of stick to the bed. But you don't have these continuous layers, and you just have the outer edges sticking down to the bed, so that the places where the force is most necessary are there, but the interior peels off easily. This also improves mass production because auto ejection is more reliable and all that kind of thing. You can take this a step further because, again, that rastering, if you're working in these corners, you can have some corners with longer streaks of materials than ones on the other side where they're turned 90 degrees. You can also cut like an X through the raft, which will break up those continuous lines so that, again, you just have material sticking to the bed, but you don't have these long shrink regions that can cause issues on the raft and other pieces of material. And you can play around with these patterns. We could probably do another video where these patterns can be very explicitly designed, because there's a lot of really cool stuff you can do with zigzags and that kind of thing that can really improve this. But that improves the raft first layer so that it's reliable, sticks down to the bed, but it's still easily removable, but still also holds down as well. All of these factors that you're playing with. Now, very lastly though, there is one more thing that we can do with the print itself to make sure it's stuck to the raft. And this is an advanced feature that requires a lot of teamwork between supplier and designer. And what you can do is now thicken the raft so that it's very thick and rigid, which can be useful because, again, if a raft is thick, it's more difficult for it to warp if you're using the correct type of materials. It can effectively have infill, and now you have a strut underneath the part. But if you are trying to stick the part really reliably to the raft with a really high warp material that, like, the little struts don't work, you can't just space it just right, all the rest of this, a thing you can do is effectively create long lines of connection so that you have this kind of Velcro disconnect feature. The way of doing this is with just hemispheres, and then make sure that each one of the interface locations is one layer thick. That simple one layer lets us break it away really easily, because one layer of printed parts will break away really easily. So you can do a hemisphere, make sure that the tips of the spaces in between the hemispheres are one layer thick, which means 0.4 millimeters, or maybe 0.5 if you want to stretch it up to, again, make sure it auto slices well and it's not like a thin wall that's ignored. But then you can have that whole row along the bottom, and then the part will break away from that whole row, but still have really, really good adhesion because it's effectively the same part. That lets you connect the piece more tightly to the raft, but still be able to break it away. So hopefully that covers raft design for you. Slicers are really bad at most features, including support and brims, and of course rafts. And we're gonna go through how to design those features explicitly in CAD itself so that you do not waste material, you don't end up fondling settings for days, and you actually get exactly what you need in a very reliable and very engineered sort of context, rather than an auto-generated hope it works kind of a way.
Almost everyone uses auto-generated supports from their default slicer in order to support parts that require it, which are a whole bunch of different types of parts. But this is kind of the worst way of doing it. So in this video, we're gonna talk about why auto-generated supports are just horrible, and also go through the multiple different solutions to either prepare for those supports or design entirely clean alternatives. Okay, so why do auto-generated supports suck? Well, at a very generic level, it's because they are the default. They are a generic solution. They are a catch-all solution. And a generic solution is fine, it works, but it always gives you kind of a generic result. This is especially true for designers who are creating parts that many different people will print on many different types of machines. If you are a designer, you don't want people to perceive your product as bad because the individual settings that they're using are not correct for that thing. You want that part to be printable just as is, so that somebody can just upload the model and print it regardless of what their device is. This also holds true for services. If you are wanting to mass produce a product or put it into a service like our print-on-demand teleport service, in that case, you want the part to be really reliable so that you're not worried across thousands of pieces of certain defects coming in. You can engineer to avoid certain common issues that auto-default, auto-generated stuff can create. So that's the reason to kind of avoid just the default support settings. It's fine if you're an individual and just doing a one-off, but for all professional use cases, you really want to tune supports in. And in order to do that, you want to be totally isolated from the slicer itself. So there's two ways to actually do this. The very first one is to prep the part to be supported. This is going through a couple of different tricks to where supports end up where you want them to be or not at all. And then the other one is to actually design the supports from scratch yourself inside of CAD or through a couple of different solutions. So let's go ahead and look at that first category. If you're prepping a part for support, obviously the very best solution is to design the part to need no supports at all. This could be something as simple as just rotating it 45 degrees. If you have a cube, chamfer the outer edge, turn it sideways 45 degrees, and now it needs no support at all. It just prints up on a corner and it's stronger, it looks better, and you have no supports anywhere that need to be removed. That's an optimal solution. You can also chamfer edges so there are no direct 90-degree overhangs, all kinds of things. And we go through all of this in a separate video where we talk about how to design parts so you don't really need supports. But if you do need supported areas, there's a couple of things you can do. Say you have something like a tooth in a dragon. We have this default model here that is just to demonstrate that. With this sort of a situation, what you want to do is actually create a support thumbtack. And you can either move this in there in a program like 3D Builder where you just position an STL and then merge them, or you can design it in CAD yourself. And basically that is to take a single little spike out of the bottom of that spike and then give it a broad lower surface. This catches all the support and gives it a nice firm foundation, and then that cone of the tooth can grow out of that. These types of pins are really, really useful because the failure of auto-generated support is that it doesn't actually touch the part. So these type of overhang pieces, when they're first growing, the tooth is just coming up like this and has nothing around it holding it vertical. It can start to rotate and fall into the support and the nest around it, so that you end up with weird aberrations on the side of the part. But if you use this thumbtack method, you know it's held all the time, always, so you don't have to worry about it suddenly kind of settling into the support and causing features on the outside of the surface that would be undesirable. But let's get into the real meat. You don't want to use auto-generated supports at all. Get rid of them, they just leave hangy-draggy messes all over the place. You want to actually design supports into your part so that you can upload it and know that it comes out exactly as you intended. In this case, what you can do is you can just design a piece of support that is offset from the part. You can use the offset tool inside of your CAD program, or you can model it, or you can use a negative inside of something like 3D Builder to kind of create it and then scale it down. There's a lot of ways of getting the modeling done, but this is basically you just design a piece underneath it that contours to the shape of the part so that it supports the part as it's being made. And that way you know that the overhang is supported exactly as you intended, you can verify it, and that's fine. The problem with this is that you are restricted to very certain types of materials and parts. It's not always universal, because if you set the settings just a little bit off, then material expansion might be an issue, the machine might still be an issue. The best solution is to give spacing of about 0.2 to 0.3 millimeters, and then test a couple of times to verify. And of course, if you were designing exclusively for a particular machine or a particular service or method, then once you know kind of the feel for it, you know the rules of it all, then you can design everything that way and you can throw up whatever you want and you know it will work. But if you're on your first try, you want to verify it after a couple of tries. Quick side bubble on the design support and the thumbtack. If you're using the thumbtack as we had in this case, you actually have to have support generated up underneath it. And while it's great for defining that support, it's still a really tall, thin piece of support, which can fall over and create a failure, which we actually ran into during this video. But if you use design support, you can actually use the support comb methodology to where you have these small sprues reaching out of the main part, holding up that support so that you know the support is really reliable and really fixed in the position where it needs to be, and you don't have to worry about the printer knocking it over and losing that support, which would cause a print failure. So again, being able to design makes you ensure that the part will print successfully. That's kind of the obvious version of design support, which is to just replace generic support with the designed support. And that's fine, and it works fine, but it is kind of a lot of work. But with design support, you're actually able to get some benefits that you otherwise wouldn't have from standard support. You can have minimized material, and you can support areas that you just need to support. Again, auto-generated will put it wherever the auto-generation decides it should go. With design support, you get to place it explicitly where it's necessary so that you get something really good. The other way to kind of prep a part to not really need support or to reduce it is to actually use a support fin. A support fin basically is just meant to increase the base contact area of the part. So with that cube, if you rotate it 45 degrees, it's fine, it's symmetrical. But what if you have something long and skinny? If we go back to our demo part, if we just rotated it around a little bit weirdly, now you don't have support on that tooth there anymore. But now if you try to print it just like that, it's gonna fall over because its center of gravity is too far to the left. There's a bunch of mass sitting out to the side that wants to fall over as it's being printed. So you want to design a support fin underneath there. And a support fin, you can design it to where it's basically just a triangular prism underneath there that is spaced off from the part. But again, you're dealing with that settling problem to where the part could fall over into the support in just that point little two space between the support and the piece itself, so it's still removable, that you don't want to actually do that. Instead, add just a few little prongs through there that are about 0.5 millimeter thick and 0.5 to 1 millimeter wide, that are perfectly horizontal so that they are a single layer into the side of the part. These hold the part stable and make sure that it doesn't fall or settle into the support, which means that you again have a really reliable piece. But here's the trick with this. You want to make sure that this support fin is also removable. In order to do that, it needs to be able to bend and flex. You can make it really thin, but if you do that, you need to give it a wide base so that it doesn't unpeel from the bed. You can make it fat. In that case, just make sure to chamfer or fillet the front of it so that when somebody is removing it, they can bend and twist and break off all of those little tines that are holding the part stable, or snip it off and get access to it. You don't want to bury them in the middle of a really thick support fin. But that's the design of a support fin, and now you're able to print the part at a diagonal angle and you don't have to worry about it potentially falling over or anything like that. You can also use these type of support fins to just give more rigidity to like really tall, thin pieces. And again, we go through this in a whole separate video. Okay, that's the overhang for the tooth. It's the one that could kind of need like a really optimized type of design. But what if you're just trying to support like a bridged area, something like a tunnel through a cube? We'll do this really simple example here. With this one, literally, since most machines can bridge 1 to 2 inches pretty readily, you don't need a ton of support in here. You can just insert a little cube. Now, many people would model just a solid cube. That's not really very desirable because it can be tough to remove depending on how big it is. You want to make sure that this part can be removed. Make sure that the top has like a 0.2 clearance and the bottom has a 0.2 to 0.3 clearance as well. This is kind of the generic sort of dimensions, but again, test based on the material and systems that you're using. But if you have a solid cube in there, do put some text on the side that says support so that post-processors know how to remove it. This is one of the cool advantages of designing support. You get to put instructions there that your customers can use. Kind of like removing shipping screws or tape and that kind of stuff inside of a machine when you receive it. Things that hold it stable in shipping, you might want that support to arrive at your customer and then they pluck it out. In that case, you want to define it as support so they can't mess it up. But if you want it to be more easily removable than a solid brick, which can be quite difficult, instead, you can actually just cut a hole through it. Now it's crushable. If somebody crushes that with some pliers, the two sides will collapse in and then it plucks straight out. That's very, very easy. Now, if for some reason you have a part that is too large to do that kind of just cut through design, because it is bridging itself, of course, then you want a solid support inside of there, that's fine. Just make sure that that support is removable, which means that you probably need the ability to twist it. So again, in this case, don't make it a solid rectangle, make sure to chamfer the edges of it, and now you still get to have your text telling people that it's support, it's more easy to remove, all of the optimizations are there. So there's a number of different directions to go with this, depending on what your actual use case is. But again, engineer it how you feel is best to accommodate the instructions, the crushability and the removability, and whatever sort of intention you want with that. You're designing support, so design it. Okay, if you're not really that good at CAD, but you just want to like use a service like Teleport, but you don't like the auto-generated results, then you can design the supports yourself without having to design them. The way this works is we're going to use the default example of Prusa. Prusa Slicer allows you to export 3 supports as a solid 3D model. And this is an interesting thing that most people are not aware of. If you go into the standard FDM settings of Prusa Slicer and then change the system over to an SLA printer, and then you can turn on tree supports and define them to be fat and thick because we're dealing with FDM parts. And with those fat and thick supports, you can generate them automatically, and now you have a really clean and pure model that can now be exported as an STL so that all your geometry is in place. It's not a tool path or exporting the G code. You're actually exporting the tree supports. They're a little bit weird because they're not always quite dense enough, but this is a really good way of auto-generating supports making sure they're placed where you as the designer intend them to be, and then you can upload them to a service or share them with your community so that they can print them, and you know that they don't need to generate supports themselves. So if you don't want to go through all the CAD, then you can actually auto-generate supports, control where those land because you're familiar with the slicer, and export those designed supports to be used by someone else. And again, the point of using design supports is to make sure that you as the designer get the result that you intended. Auto-generated supports are fine if you're at home or in your garage. Go quick draft them out there and pick at them for 3 hours. Be my guest. But if you are distributing it across thousands of people or making thousands of parts, then you want to optimize it. And auto-generated generic solutions are not the way to get to an optimal solution, to where you have a really good, crisp result for any of your users or any of the buyers of your product. So hopefully this video was useful to you about how to design supports so that you're not beholden to the auto-generated gods. And you can check out our other videos to see other nifty solutions about how to design those supports as well. And hopefully that will help you improve how you create your own 3D printed products in future. Have a great day, everybody.